All right. Today we're going to talk a little bit about some SATCOM type measurements. If you're not in SATCOM, more specifically, we're talking about wideband measurements that are generally higher in frequency. Typically for satellite, we're talking around Ka band. And in particular, we're going to talk a little bit about correction techniques that you can use to enable lower cost of test type measurements rather than some of the a little bit more expensive methodologies. And we'll talk a little bit through some of the trade-offs there. So here's kind of the overview. So we're going to just take a quick look what's nonlinear distortion. The types of signals we're going to talk about are signal stimulus signals. Focus more on noise power ratio measurements. Again, in the satellite space, this is fairly popular for transponders. And then finally, we're going to look at some analysis techniques and look at some of the things that we typically do to make those types of measurements on the analysis side. So what are the linearity concerns in satellite communication? So you can see here we have a transponder, and typically what we have is see if I can point here. So in this channel, we have multiple channels, and in this whole band, we actually have what we have typically is some spectral regrowth or some distortion that folds over into an adjacent band. And that issue obviously is bad for our communication channel, and we want to make sure that things like amplifiers perform nice and linear and do not get those distortion products so that we have usable bandwidth. So real quickly, I think everybody kind of understands what nonlinear distortion is and spectral regrowth is, but you can see here we have some spectral regrowth, and that typically happens when we're really trying to push our amplifier into the nonlinear range, and you get this out-of-band energy that, again, bleeds into adjacent channels. So obviously we have multiple signal bandwidths, different amplitudes and modulation, and these products eventually add together, and then it becomes difficult. So we use a methodology, or customers use a methodology called noise power ratio to determine what that out-of-band energy is and make a metric on those nonlinear elements in their system. So again, noise power ratio, what are we talking about? Typically you want really nice defined channels, and then you measure the regrowth or the energy that falls into this notch here. So we have a specified bandwidth, and typically you want a lot of depth, so you insert this signal into an amplifier, and then you have some spectral regrowth component. You take the ratio of that, and essentially that's a noise power ratio. So how do we traditionally make these measurements? A lot of times customers, they take a wideband signal and they use a notch filter or band stop filter, and they notch out part of that waveform. So you can see here that would be this area here where you have a band stop filter that notches out a region, and then you can use that as a stimulus signal to make these types of measurements. What problems you run into is these are typically high Q filters, and again, you still have some rounding issues there. So we're going to talk about some techniques other than the analog approach where you get a wideband noise signal and you use a notch filter. Some other techniques that you can use to be a little more effective on creating a nice large depth notch filter. So on the left here, I have a picture of an analog approach with a notch signal for NPR stimulus, and then on the right we have a digitally synthesized signal. And specifically, we're talking about really wideband signals with really large depth between the top of the signal and the null. And what's nice about that is it's very repeatable, it's easier to set up, and it's a lot better as far as fidelity goes in many cases. So here's an approach. You take a wideband arbitrary waveform generator, you upconvert that, and then you have your DUT, you stimulate the device under test, and then you can make your noise power ratio measurement with something like a signal analyzer. And here we see that before you have a specific notch depth that's pretty deep, and then when it goes through the device under test, that adds spectral regrowth and nonlinear distortion, and now you have added growth there. So what are some things that you can do as a customer or as a satellite test engineer to help mitigate this. A lot of times when you start creating basically what I was showing before in noise power ratio, you create a whole bunch of tones, you add those tones together, and those tones become your effective channel. So here I'm showing a lot less tones. I think I'm showing about 8 tones. But typically what happens when you do this is you get a lot of nonlinear distortion products. So kind of a trick that you can do is you can actually create destructive signals that can knock down these spurious problems, as well as LO feed-through and other problems that you may have in your signal channel. So typically when you do this type of application with arbitrary waveform generator, you're going to see these types of products, and the counter to that is a technique that is typically used to knock these down. So it's a mathematical approach to calibrate and correct. And in this same process, you can actually correct and enable a nice linear flat top, which is another desirable trait of these types of waveforms. So a new approach is a new arbitrary waveform generator that we have that enables even wider bandwidth. So we can go 12 gigasamples per channel or 8 gigasamples per channel, which can give us up to 80 dBc of dynamic range. And you're really, again, looking for that large notch depth. Again, up converted, and then we go feed this one directly into a scope. So there's 2 different approaches. I talked about the one with the up conversion process, and that's the top one here, where you actually have analog differential IQ. You output it to a IQ modulator. In this case, it was a signal generator, and then output that, of course, into your device under test. Again, that creates some issues because sometimes you have cables that are not exactly matched, so you have IQ problems. Again, you get some distortions in the IQ modulator, so you start to have some problems there. Another approach is the direct up conversion approach, where it's all done in an arbitrary waveform generator. There's a digital analog converter, and it goes straight into your device. And the advantage of this is that you get much, much cleaner. You can see there's some spectral regrowth here, whereas in this case it's much clearer. And again, how to combat that is some correction techniques, some algorithms that you can use to combat that. So this kind of shows the 2 cases. So one case, this is using a digitally modulated signal, but in one case we have an arbitrary waveform generator with some up conversion, and we use the exact same waveform in the second case, and you can see the difference between the EVM is about cut in half using the direct approach. So again, if you can use the direct approach, use that. The problem that usually you run into is that you can't really make high frequency measurements, so you do need the IQ modulator to do the up conversion. So on the analysis side, I'll briefly talk about it. So we've got a couple different waveforms here. So I have a noise power ratio measurement here, and then we have some CCDF curves, which is another thing that I think people can use to kind of determine with a lot of the newer waveforms what peak to average power ratios create, or a lot of issues in our amplifier chain. I have one that's totally constructively created and one that's totally destructively created. So depending upon how a bunch of tones add together, you can see different problems, nonlinear issues in an amplifier. So a couple different measurements, but we'll talk through some more methodologies here. So basically what I'm going to talk through is using you can use this on different applications, but basically all along your device under test chain, you can actually make some of these types of measurements. So some of the traditional approaches, you can use a signal analyzer. Typically you're in the 80 dB-ish range with a direct digitizer. And then you can also use a wideband down conversion approach, where you down convert from a signal analyzer into an oscilloscope. And then another option is to go straight into oscilloscope. And now that oscilloscopes are going higher and higher in frequency, you actually have a choice to make between going directly into an oscilloscope or using some sort of down conversion option. So the down conversion option is a little bit less expensive, so I'm going to talk a little bit about some of those trade-offs and some of the things that you can do here. So basically here we got calibration, where you can do amplitude flatness calibrations and phase linearity. I'm showing an EVM plot here that just basically shows the 2 components adding together, the 2 components side by side. So you could have on the I and the Q axis, you could have both phase and amplitude variations here. So you can add that up and you can break that down. So down conversion approach, obviously going out of a spectrum analyzer and into an oscilloscope. And one of the advantages that we like to show is some way to correct these types of applications and then also make the measurement. So the difficult approach you typically have is you you have some sort of correction routine, and then you got to figure out how to make the measurement. So either you're writing a lot of software to do that in one application, or you have to post-correct after you make these types of metrics. So something like EVM becomes fairly difficult to do with the corrections. So here we're setting up a down conversion, as you can see here, and then in the next stage, you take a signal generator, and this is the amplitude correction approach, where you just take a signal generator and you sweep via amplitude across the band that you're interested in. And then on the next slide, we're going to take the inverse of that correction. You can see there's the correction in 1.5 dB per division over a span of 900 megahertz. That's the frequency response, essentially, of the IF, of the down conversion process. You invert that, and you apply a correction, and now you have a flat, nice and linear application here where you can now make a more linear and equalized measurement and at a much lower cost than maybe going directly into a really wideband oscilloscope. Again, now you can, after you've done that, you can also make a measurement, so you can see typical satellite signals like APSK and SOQPSK. You can make that inside of the same application and now make your measurement. So a lot of tools nowadays have the capability to do both of those things. I suggest taking advantage of that. And then I'm going to walk quickly through some of the things that the paper kind of highlights here. And again, the paper that's on the DVD is much longer and has a lot more detail on how some of these things are made. So I highly suggest you pick that up so that you can go into more detail on this specific paper. But again, we talked a little bit about nonlinear behavior, and if you're not familiar with that, again, I covered a lot more of that in the paper. I talked a little bit about multitone and NPR signals and how we can create those and make them and synthesize them in a much more higher fidelity mode with a lot larger notch depth and a lot more repeatability than in traditional approaches. And then some techniques to make measurements with a signal analyzer that are a lot more cost effective than traditional measurement, or excuse me, than a direct approach, which again is better in fidelity but costs a lot more money. So there's a lot of different methodologies you can use to make these higher frequency wideband type of measurements. In this case, we use the 900 megahertz wideband measurement here. So that was the NASCAR version of this paper. So any questions?